morning. How are you?
Good morning, doing good. How are you?
I'm pretty good. Oh, it's good. It's almost the end of the week.
Yeah.
Then I just start the cycle all over again. But let's see. Sierra College has Monday off. So if you're also in my discrete structures course on Monday and Wednesday, I won't have class that day. And some students are a little confused because when they went to high school or elementary school, they got the whole next week off. And so some of them mistakenly believe that they have the whole week off here, and they don't. They just have one day off. Actually, we have 2 days off. We have Friday and Monday, but we don't have class Friday anyway. How are the rest of you doing? Let's see. Good morning from good morning from California, and hello to people in Europe and India, where it's afternoon or evening or nighttime. Well, are there any questions about the material we've covered so far? Well, today's going to be kind of a fun day. We're going to start off with going over the game assignment that we're doing for this week, and then we will get into some image manipulation. So I'm going to show you how to load an image into memory, and then we could do something with it, like maybe flip it upside down, or we can, what else could we do? We could rotate it, darken it, lighten it. There's a bunch of things we could do to it. So why don't we start off with just looking at the assignment. So we're all the way down here. Where are we? Here we go. So in this game, or in this assignment, you're going to be implementing a simple puzzle game called Reverse. It uses an array of integers to store the state of the game. So we're going to learn how to shuffle or randomize an array, learn to determine whether an array is sorted, reverse the elements of array, and implement reusable functions. So the gameplay is pretty simple. The board starts out with a certain array size, and the numbers in it are all jumbled up. So if the array size is 10, it starts out with the numbers 1 through 10, but they've all been jumbled up. And the goal of the game is to sort them so they go from least to greatest. But you can only sort them by reversing a subset of the array. So you could reverse, let's say, the first 3 elements, and then it will just flip the first 3 around, and it'll leave the remaining 7 the same. So with successive reversals, you should be able to get the array sorted. I've given you some starter code. We'll be able to scroll through it a little bit. Actually, let me go ahead and download this. Just highlight this whole thing. And we'll bring it into our programming environment. So let me make a new file here. Just paste it in. So the rest of the assignment page here talks about the various functions that you'll be writing. I'll just scroll through the code and walk through these with you as well. But I think there's 5 or 6 that you need to write. They all have to do with arrays. Let's see, where can I start with this? Let's kind of look at main here. So the first thing it needs to do is it's going to seed the random number generator. This is just the standard seed it with the current time. We're not going to do anything more fancy than that. Then it's going to ask the user how large should the board be? Minimum of 3, maximum of 20. It's going to call a function named getInt, it's passed in a string, the minimum number, and the maximum number. So that's one of the first functions that you need to write, is called getInt. I've written the function prototype for it right here, but I don't think that function is anywhere in here. Oh, here it is. There's a stub for it down at the bottom. So that a stub means I've written just enough of the function to get it to compile, but it's obviously not complete. So you're going to need to replace the code that's in here, which is just a placeholder code to return something, with a function that will prompt the user, given the prompt here, and ask the user to type in a number, and then check to make sure the number is in between the minimum and the maximum. If it's not, loop back and prompt them again. Once the number is between the maximum and minimum, then go ahead and return that number back to the caller. You'll probably need to get that one working first. The next thing the program does is it creates the board, and using the length that the user typed in, it creates an array of that length. And then it fills the board in. So we pass in the board and the length of the board, and what fill board does is it just fills the numbers in from 1 up to the board length. So if the board length is 5, it fills in the board with the numbers 1 through 5. So fill them in order. And then shuffle the board. So it's going to call shuffle board here, and then it's also going to check to make sure that it in fact has been shuffled, because the problem with calling shuffleboard is there's a very minuscule little chance that it might actually not shuffle it. It might just shuffle it and then it ends up being in the same order it was before. So it's going to check to see if the array is sorted, and if it is, it'll shuffle it again. What I recommend you do is just remove the comment for the one single shuffleboard and make sure that's working, and then you can remove the comments for the rest of the statements once you get is sorted also working. I've got these lines of code commented out so that you can tackle this program a little at a time rather than trying to do the whole thing all at once. Start at the top. Get int working. Next, get fill board working. And you might want to insert in here a statement to print out the board. And in fact, I think that's one of the functions you have to write. Oh, it's print board. So you may want to get print board working as well. And then insert that line right here after fill board, and just make sure you get an array with all the numbers in the correct order. Then it goes into a loop, and it asks the user, how many should I reverse? And the number should be between 2 and the length of the board. We're reusing the getInt function that we wrote above, so we can use the same function for both purposes. It will then reverse that portion of the board. You'll need to fill this in with the appropriate arguments. Then print the board out, and then check to see if the board is sorted. If the board is sorted, the game is now over, and it will break out of the loop. And then finally it'll say, you won. Okay, so that's the assignment. Now let's go and show you how to do some of these. I won't actually do the assignment for you, but I'll write some simple programs that use some of these functions. So which of these have we already done? We've already done, well, you should be able to do something like getInt. That should be fairly easy to take care of. You should be able to fill in an array with the numbers 1 through the length of the board. You actually did something very similar to that in the fill array program that you did last week. So I think maybe the first thing we need to take care of is, how do you take an array of numbers and randomize them, shuffle them up? So let's work on that first. let's make an array, and let's just, without running a loop, let's just fill it in with the numbers. Let's do like 1 through 10. And now I want to shuffle these. So here's a quick and easy way to shuffle an array. Pick 2 random elements out of the array and then swap them. And then pick 2 more random elements out of the array and swap them. And do that some number of times, and that should randomize the array. Does that make sense what we're doing? So if we have the numbers, let's do 1, 2, 3, 4, 5. We roll the dice. We pick a number between 0 and 4. This is number 0, 1, 2, 3, and 4. Let's say we pick 1 and 4. So we're going to swap these 2 elements here. So we'll end up move this one aside, move this one over here, and then move that one over there. So we just swapped 2 elements of the array. And then pick 2 more to swap. Maybe it's 2 and 0. Move that one out, move this one over here, and then move this one over here. And then pick 2 more to swap. Let's say it's 4 and 3. All right, so that's the general idea. Let's pick 2 random elements and then swap them. How many times should we do this? How many times should we swap elements of the array in order to pretty much ensure that we've got a good shuffling? What do you think?
I used that same method, and I picked 100 times, and I just picked that to try, and it seemed to work for the up to the length of our board, 20. So that's what I stuck with.
So I've heard a good rule of thumb is to pick about 3 times more than the length of the array. So if your array is 20, I would do this 60 times. If our array is 5, I'd do this 15 times. I mean, we could probably actually get a pretty good shuffle if we just do it n times, right? If our length of the array is 5, if we just do this 5 times, it'll probably get us a pretty good shuffle. But doing it 3 times as many is probably a little bit better. And in fact, you may even use this technique when you're shuffling a deck of cards. You might shuffle it maybe 3 times, right? To just kind of like ensure. Now the problem with shuffling your cards is it's not really a good shuffle. You're not swapping cards. You're just interleaving them, right? In kind of a random way. But the 2 halves of the deck are still in the same order. Does that make sense? Right? You split the deck in half. Now you've got 2 top cards. Those 2 top cards are still going to be among the first cards, right? You know, so each half of the deck is still in the same order within the shuffled deck. So that's why you have to do it several times in order to really break up the ordering. We're doing not anything like a card shuffle. It's almost literally like taking the 2 halves of the deck and then randomly picking cards out of each one and just swapping sides. Okay, so we're going to do this 3 times 10, 3 times the length of the array times. First step is to pick 2 random elements. Let's call them A and B. So we're not picking the values out of the elements, we're just picking random index numbers. So we're picking a random number between 0 and 9, and another random number between 0 and 9. How would we do that? we've got the random function here, but what do we do in order to get a number between 0 and 9?
For 0 to 9, we have to then do modulus 10.
Correct. So modulo the length of the array. Do this thing for A and B, and now we're going to swap elements A and B. In order to do a swap, we need to take one of those elements and move it aside, then copy the other one into the first one, and then take that first one and move it back into position. So we'll take element A and move it into a temporary variable just to store it away. Then you take element B and move it into A's position. And then you move the temp back into B. So it's almost like you've got A, B, and temp here. So you do A into temp, B into A, and then temp into B. The question is, why aren't I using size of array? Because the size of gives us the number of bytes in the array, which would be 40 in this case. So then we have to divide by the size of each element, and this quickly gets more complicated than it's worth. At least for a very quick little program to just demonstrate how to shuffle the array. Okay, so let's do this swap here. We go int temp equals array A, and then array B equals array A, and then finally array, oh, I got this wrong here. This should be A, and this should be B. And then finally, we're going to print out the array. Okay, so let's look at the program. We're going to start out by initializing the array with the numbers 1 through 10, and then do this 30 times. We're going to pick two random elements, swap them, and then loop back and do that again and again and again, and then finally print out the array with the numbers with spaces in between them. The last thing we need to do is make sure that our random number generator is properly seeded so that we will get a random sequence every time we do this. If we don't seed the random number generator, we'll get the same random sequence every time, so it won't be random at all. And then our array will end up being shuffled exactly the same way every time we run the program. So in order to use the random functions, we need to bring in standard library.h, and in order to use the time function, we need to bring in time.h. Okay, so I've saved it. Let's compile this and run it. And there is our shuffled array. And every time we run this, we get a different shuffle. So one thing to notice about this is occasionally this program or this algorithm is going to pick the same A and B. It's just a random number. The random number generator does not ensure that it always picks unique numbers. So is that okay? Is it okay for, let's say, element number 5 to be swapped with itself? I'd say yeah, that's okay. And in fact, a random number generator that always ensured that it produced unique values is really not very random. I mean, imagine if you had a coin that you flipped and it ensured that every time you flipped the coin, it did not come up the same way it did before. So you flip it and it comes up heads, and you flip it again and it says, okay, I'm going to make sure I don't come up heads to make sure it's really random. And so it comes up tails, right? And then you flip it again and so it's, okay, make sure it doesn't come up tails. I'm going to make it heads. So that wouldn't be very good at all. You know, and imagine you had a dice also that rolled the same way. Once you roll a 6, it'll never come up a 6 again until you've rolled all the other numbers. So that's not very random at all. So it's in fact important that a random number generator occasionally picks the same number again. Okay, so that's a very easy way to randomize an array. Just pick 2 elements, swap them, and do that. Good rule of thumb is 3 times as many as the number of elements you need to randomize. Okay, so that should give you information to be able to write shuffleboard. You also probably know how to write printboard. Reverse, we went over last time. However, this is not going to be a function that reverses the entire array. It's going to be a function that reverses only a portion of the array. So you're going to pass in a third parameter. You're going to pass in the name of the array, how long it is, and then how many elements you actually want to reverse. So the last function you need to write is sorted. How would you find out if the array is all sorted? So basically you want to know if we have 5 elements, is it back in this order? 1, 2, 3, 4, 5. So one way to do it is, as just been suggested, as you run through the array, make sure each element is more than the one before it. So if you've got 2 here, look at the previous one and make sure the 2 is greater than the one just to its left. And then make sure this one is greater than the one to its left. And make sure this one is greater than the one to its left. And if you ever find one where that's not the case, then you know it's not been sorted. And the nice benefit of doing it this way, of just making sure each element is bigger than the one before it, is it does not depend upon the array being consisting of numbers that are consecutive. All we're checking is to make sure that every number is bigger than the one previous to it. So that means we could have an array like 1, 6, 8, 9, 12, and it will still check to make sure that it is sorted by doing that algorithm. However, we could make it a little bit simpler. Our particular array has the numbers consecutive, and they start at 1. What could we do in that case? So given that we know what the array is going to look like, we know it's going to be 1, 2, 3, 4, 5, what's another way we could do it?
So you could check if the value at each position is the index plus 1.
Yeah. So the value at index 0 is going to be a 1. And the value at index 1 is going to be a 2. So you could just do it that way. Just make sure that each element is 1 more than its index number. And if you ever find something that's out of place, you know it's not sorted. So a couple different ways you could do this. There was a question, let's see, should I be using rand instead of random? And we had this discussion last time. What's the difference between rand and random? And a very nice user posted a long comment on the video about what the difference is. And I was actually wrong last time about the difference. So I appreciate that someone was able to set the record straight. So rand and random, one of them is defined by the ANSI, A-N-S-I version of C, and one is defined by the ISO version of C. They're very similar, but one of them is not ANSI, POSIX, which means it's a Linux compatible library. So one of them is POSIX defined and one of them is ISO defined. But internally, most standard C libraries just implement both functions the same way. But internally, it's doing the same calculation. In fact, most likely one is just calling the other. So both functions are there for compatibility purposes, but internally they're just the same function. With one slight difference. One of them returns a long, and one of them returns an int. I think random returns a long, and rand returns an int, which means that on things like a 16-bit computer, rand is only going to produce a 16-bit result, whereas random will produce like a 32 or 64-bit result. Otherwise, they're internally the same. So that thing about one being like slightly better than the other, I said last time, was probably not correct. It was based on old information I had, which was rand produced a smaller set of numbers and random produced a bigger set of numbers due to some internal differences in the way it calculated the numbers. Like this commenter said, these days they're just the same function, but in the past they may have been different functions in which rand produced numbers with fewer bits of precision than random did. Anyway, so now we know that both of them are essentially the same, and as long as you're staying within the bounds of an integer, an int, then they're both essentially the same. Okay, any other questions about the game? So as far as order of operations here, order of doing it, get int working, get fill board working. Then I would actually jump ahead and get print board working, because you kind of need that for debugging purposes. Then do shuffle board. And then probably work on reverse. And then finally is sorted. And is sorted gets used in two places. It gets used within the loop, and it also gets used outside of here to make sure that the board you start with is randomized. I guess I must point out here that this is probably not the best way to ensure that the board is randomized, because there is a very, very slim chance, and I say very slim, but these are the things that programmers have to worry about, very slim chance that you may shuffle the board and then it comes out to be sorted again. And so you go into this loop where you shuffle it again because it's still sorted, and then you end up having the same board again, not sorted. And you may, again, very, very slim chance that it may get stuck in a loop and forever be trying to shuffle the board when in fact it can't. Like I said, it's very unlikely for this to happen, but this is where software, mission critical software, ends up breaking one day, when it gets stuck in this loop because it's not ever able to actually shuffle the board. And so if you go and Google around for good shuffling algorithms, there are actually some better ones that will ensure that the board is shuffled at least. At least something is out of place. So you may want to take a look at that. But we're not worried about that. Most likely, you may end up with shuffling the board. It ends up being not shuffled, and so you shuffle it one more time, and now it's shuffled, right? So really, on average, shuffleboard is going to get called once. Maybe once in a long while, it'll get called twice. That's okay. Okay. Any other issues with this?
I have just a general question.
Mm-hmm.
When you're doing the for loop for shuffling,
Yeah.
and you're creating three integers or
Mm-hmm.
declaring three integers within the loop.
Yep.
There's a, b, and temp. Does it matter if you, from a memory standpoint, does it matter if you declare those integers within the for loop or outside of the loop?
No.
Okay. So each time the loop runs and it declares and allocates space for that integer, then at the end of that loop, it's releasing that memory.
So what the compiler actually does is it goes through the function and learns the names of all the variables that will be created and then allocates space for them ahead of time. When you come into the body of the loop, it just recycles that space that's already been set aside. So
Okay.
it goes out of scope in the sense that if I write a line of code in my program that attempts to access a, b, or temp outside of the loop, the compiler will say, hey, the variable's out of scope, you can't use this. But in reality, the variables are still there in memory. It's just that the compiler has sort of recorded down a piece of information that says, at this point, those variables should be invisible, so I'm not going to let the user try to access them. However, if I did some tricky stuff inside the loop here or outside the loop and went looking around on the stack, I would find those variables. Not by name, but I'd find their values sitting around. Does that answer your question?
Yeah.
So
thank you.
it doesn't matter from a memory perspective whether you create those three integers inside the loop or outside the loop.
Okay. Thank you.
It'll still set aside the memory for them. Now, so where that could differ slightly is, let's say you created an array of different sizes. So let's say you created an array of different sizes inside the loop, then yes, it will dynamically allocate new space for the array every time. But these are just three integers. It knows what the sizes are ahead of time, and it'll just set aside the space for them.
Okay.
Yeah, good question. Okay, so let's see if we can do something with some images. Now, so what I did was I wrote a quick C program that will act as a wrapper around an existing library that does image manipulation. So there's, on most Unix or Linux systems, there's a library called GD, graphics. I don't know what the D stands for. Anyway, it's a graphics library that allows you to do things like load a file from, load an image file into memory, and then get access to the individual pixels in the image, and then be able to write new pixels, save the image. And from a beginner's point of view, the GD library is a little bit difficult to use. And so what I wrote is something called a wrapper library that takes the internal functions from GD, and then I wrote some to make them a little bit easier to use. So it just, internally it's just calling the GD library functions, but it's doing it in a way where I can present sort of an easier interface to those functions by using arrays and integers that we're used to, not things like structures and constants that we're not used to yet because we haven't learned about those things. So I posted those two files on a Dropbox folder where anyone can get to them, and the address was, I made a bit.ly link out of it, so here's the link. It's bit.ly/c-image-library up here. So if you go to that, you'll end up on Dropbox. And then there's two C files, a C file, a header file, and then a couple of images that you can use. And then here's where actually I ran into a little bit of a problem. How do you get them into your programming environment? So there's two ways you can do it. One is you can just drag and drop the images and the files directly into your file browser over here. And, you know, I'll be honest, that worked for image.c and image.h. And then I tried to bring over the picture of the burger, and it said, give me that little plus, like, hey, I'm going to do this. And then it said it was uploading the file, and then nothing appeared. So I'm not sure what happened there. And then I tried it for another file. Like I did this whale one here, right? And that one didn't work. But when I did this the first time, it worked just fine. So I'm a little confused about what happened here and why this is not working. So I'll try to figure that out. I'm not sure what's going on, but in order to get this going, I need to get those images into this environment. So I'm just going to go ahead and transfer them. I'm going to use a file transfer program to just get them right in here. And let's see, how am I going to do this? See, normally I would just do this, right? Boom, uploading, and then nothing. Very strange. Well, let me see if I can get these files in here. So, do I have this here? Oh, yeah. Okay. Hang on. Just give me a moment. There we go. And then I have one more to transfer. Good. Now I just need to move them to the right spots. Awesome. Okay, so here they are. Oh, I see what's going on. Aha! That actually gives me a little clue. I need to close this for a second. Close that. Over here. Relaunch this. What happened is my login session, for my authentication session had timed out. And so that's why I couldn't upload the files. Another thing to work on this summer is squash that bug. Anyway, so we got a picture of a yummy, yummy looking burger here. And we've also got this picture of a scuba diver with some fish. Okay, so I have this C program, and you can see it's pretty long and complicated stuff. So when somebody gives you a library like this, it's actually not usually a good idea to go look at the C code first. It's a better idea to look at the H file, because that just gives you things like the names of functions and any constants that they have declared. So let's take a look at some of these. We got load PNG. You give it a file name, and it returns an image to you. And then we've got save PNG. You give it an image and a file name, and it saves it to a new file. We've got functions like get width and get height, get pixel. So you give it an image, an X and a Y coordinate, and then it will give you an integer representing that pixel. And then we've got functions like get pixel red, get pixel green, get pixel blue that pull out the red, green, and blue components from that pixel. You can also get an entire array. So you pass it an image and a pixel or an integer array, and then it fills in that array with all of the pixels from the image. And then also one that will give you a 2D array. You can set pixels. You can set pixel RGBs all at once. So rather than setting the red, green, and blue separately, you can set all three of them together. You can create a new image, and you can also transfer a array of pixels back into an existing image. Okay, so that's all kind of complicated. So let's see if we can get something simple working. When you're working with a new library, it's often a good idea to try to write the simplest possible program you can do, just to kind of show that things are working okay. So I think for us, the simplest thing we could do would be to see if we can load an image into memory and then save it back out as a new name and just make sure we get kind of a copy of that image. So I need to include image.h, which is the header file that comes with this library. Okay, so the first thing we're going to do is we're going to load the image from a file and then save the image to a new file. That's all. It's just something very simple. So to load the image from a file, we're going to create a variable called img, which stands for image, whose type is image. Now, that's a type that is declared by image.h. Don't worry about what it actually is. Just know that it's something that exists, and we can create variables of that type. All right, so let's load in that file, and then let's go ahead and save it. So that's it. Uh-oh, I've got a problem here where the GD library is not apparently on our system. So that's another thing I gotta fix. So let me go ahead and quickly fix that. I'm guessing at the package names here. Oh, got it. There we go. Sorry, I should have set this up ahead of time. So if you're in my course and you want to set this up, here's what I did. I went sudo apt update and let that run. And then I went sudo apt install libgd-dev, and then it installed a whole bunch of packages that allow us to do graphics manipulation in C. See, is this done? Not yet. So what were those two commands? Lib apt update, and then sudo apt install libgd-dev. This control C here was just so I could abort the command without running it. Don't type that in. right? So here's the command to type in this, and then this. Let's see how we're doing over here. Okay, we're done. So let's try compiling this program. Oh, and then we need to link it with the GD library. Oh, I see what the problem is. Okay. All right, so the problem here is that we have two C files we need to compile, but we're only compiling one of them, and then the linker says, I don't know what this load PNG and save PNG functions are. So we need to go clang image1.c and then image.c, which is the file that I provided, and link into the GD library. There we go. So when I run this program, I should end up seeing a new file appear over here. And there it is, right there. So let's click on it and see, did we get, yes, it's the same as this one. So that's kind of good to know, that we're able to load an image into memory and then save it out to a different file. All right, so let's see if we can do something interesting to this. So I think the first thing we want to do is let's just see if we can darken this image. So we're going to take every pixel in the image and we're going to reduce it by a certain amount. Now, you may know that an image is made up of a bunch of pixels. So each one of these pixels is made up of 3 color components: a red component, a green component, and a blue component. And each one of those is a 3-bit quantity. Those 3 8-bit quantities then just get squashed together, and they make one 24-bit number. So the red number is stuck right next to the green number, which is stuck right next to the blue number, and then that just becomes a 24-bit quantity, which fits nicely into a 32-bit integer. So this load PNG function, for some of you asking, is more than just simply opening the file. It also calls the GD library to create the image behind the scenes. So it does open the file, but it also creates the image. And so that's the purpose of the wrapper function, is to take all this busy stuff and turn it into something that's easy for you to use. Oh, you didn't see what I was doing over here. Here, this is what load PNG looks like. Right, it opens the file for reading. It then calls the GD library to create the image from that PNG and then returns the image. Okay, so what we need to do in order to be able to work with this image is, now that we've got the image loaded into memory, we now need to convert it into an array of integers. And this is going to be a 2-dimensional array. It's going to have a height, and I point the arrow down because in computer terms, this pixel up here in the top left corner is the 0, 0 pixel. So this is the beginning of the image. So the image works its way downward, and it also works its way to the right. So it's got a height, and it has a width. In order to be able to create this array of pixels, we need to find out how big is this image? What's the dimensions of the image, so that we can create the array of pixels ourselves, the correct dimensions. So we'll go int width equals get width, pass in the image, and it gives you back the width. And then we'll do the same for the height. And then finally we'll create an array of ints to hold the pixels. So this is going to be a two-dimensional array. So you do two sets of brackets. The first bracket is going to be the number of rows. That'll be the height. And then the second set of brackets will be the width of each one. So arrays in C are declared in what's called row major order, which means when you arrange the memory for an array, it's not actually stored in a two-dimensional grid. It's stored in a one-dimensional grid, a one-dimensional line. So you've got the first row of pixels in memory, arranged consecutively. And then the second row over here is actually brought up right behind the first row. So the second row lives right here. And then the third row lives right behind that. So every row of the two-dimensional array is then brought up behind the previous ones, and you end up with just one long line of, in this case, pixels. So it's called row major order because it's stored in rows. And that's why we have to put the height of the array first, which gives us the number of rows, and then the second number is how wide is each row. Maybe while we're at it, let's go ahead and print out how big the image was. At this point, I'm going to save it, compile it, and just make sure it works. So it says the image is 1024 by 768, and that seems reasonable. Those are pretty common dimensions for an image. So now that I've got my array of pixels, I now need to fill them in with the pixels from the image itself. So right now they're just an array of garbage values. So I need to fill them in, and there's a function to do that. Get image 2D array. You pass in the image and the width and the height and the name of the array. Okay. So now what we're going to do is we're going to run through that array, and we're going to take each one of those pixels and darken them. So there's two ways we could do this. We could either just subtract off a constant amount, or we could divide the pixel values by some constant amount. Which one do you think would be better? Should we take the pixel value and just subtract? And if we want to make it, let's say, half as bright as it was before, should we just subtract like 128? Or should we divide? What do you think? Well, if we subtract, then there's a possibility that we might subtract too much and make the number negative. You can't have pixels that are negative. So a better solution is to divide. If we divide by 2, then no matter what the value of the pixel was, we're always still going to end up with a positive value, even if it was 0. So let's try that. In order to make each pixel darker, we're going to have to write 2 loops, one to run through the rows of the array and one to run through the columns of the array. So I'm doing y as the outer loop because that's going to run through the columns. Sorry, not the columns. It's going to run through the rows. And then within that, you do the X. And then let's just make each pixel half as bright as it was before. Again, this looks a little strange. We're used to indexing into a Cartesian coordinate by doing the X value first and then the Y value. But because the array is stored in row major order, we have to do the Y value first and then the X. Okay, so we got all the pixels divided by 2, and now we're going to, now what we have to do is we have to transfer that array of pixels back into the image. So instead of putting it back into the image, let's just create a brand new image and then transfer those pixels into it. I'm going to call a function called newImage. You pass it the width and the height, and it goes and it creates a new image in the computer's memory. And then we called it newIMG. And now we need to transfer those pixels back into there. And then finally, we're going to save it. Okay, I think that's our program. Let's give it a try. We'll compile it. Oh, we got an error here. Oh, this name is incorrect. Let's fix that. There we go. And now, the program ran. It told us the dimensions of the image. There were no errors. Let's take a look at new burger. And oh, that doesn't look right at all. What happened there? What do you think happened? Why does it look so weird? Here's what the original one looks like. And here's what this one looks like.
Because we did only a single calculation when we were darkening it, we should have darkened R, G, and B separately.
Correct. We took that 24-bit number, which had the red, green, and blue components side by side, and then we just simply divided it by 2. What we should have done was divide the red component by 2, the green component by 2, and the blue component by 2 separately. So we would have to pull those pieces out, divide by 2, and then put them back in. So we need to do a little bit more work than just simply dividing each pixel by 2. We got to extract out the red component, the green component, and the blue component. So we can do that as, let's say, int red equals get pixel red. You pass in the pixel that you want to do, which is pixels y and x. And then we'll do the same thing for the green and the blue. I'm just going to copy and paste. Then we divide each one of those by 2. And then put them back in. Okay, so we pull the red, green, and blue components out of each pixel. And so get pixel red, it reaches into that 24-bit number and it pulls out the 8 bits corresponding to the red. Green pulls out the 8 bits corresponding to green, and blue pulls out the 8 bits corresponding to blue. Then we divide each one of them by 2 and then reassemble them back into a 24-bit number. This should have been set pixel. Here we go. Now let's run it, and we'll take a look at our burger, and that looks better. Here's our original one, and here's our new one. It's just darker. So that is much, much better. So any questions about that? So what's going on here? What's going on with that get pixel red, green, and blue? So as I said, a pixel is or has red, green, and blue components. And they're just simply arranged as side by side as a 24-bit number. So this is 8 bits, 8 bits, 8 bits. This one here is red, this one is green, this is blue. So inside of each 8-bit component are 8 ones and zeros, and I'm just going to put some random ones in there. There we go. And so that becomes our 24-bit number. So really it's 3 numbers, but they've been squashed together to become one 24-bit number. So how do we pull out the red, green, and blue components? So C comes with a set of operators called the bitwise operators. There's AND, which is just a single ampersand. You've probably seen the Boolean AND, which is 2 ampersands, but this is called the bitwise operator. There's OR, which is just a single bar. There is right shift and left shift, and exclusive OR. So the way the bitwise operators work is you take 2 numbers and you can apply one of these operations to it. Like if I use the right shift, if I take the number, let's say 100111100, and I do right shift by 3, then it takes this number here and it shifts everything over by 3 bits. So these 5 bits over here will end up moving down, and these 3 bits over here will end up going away. So we end up with 10011, and then some zeros have come in to fill in those 3 positions. So it moves everything down by 3 bits. So that's how we can do things like get the green component. We can extract out these 8 bits over here and then shift them down by 8 bits. And that'll move it into the position where it is now just a single 8-bit number. Same thing for the red. We can pull out these 8 bits and then shift them down to the end so we get just a single 8-bit number. So how do we extract these pieces here? Well, that's where the things like the ands and the ors come in. So if I have a number like, again, 100111100, and I do and let's say 0, 0, 1, 1, 1, 0, 0. That's only 7, so let's put another 1 on there. Let me just move these down here. 0, 0, 1, 1, 1, 0, 0, 1. And we're doing an and. And then you just look column-wise, you do an and operation between pairs of numbers. So 1 and 0 is 0. 0 and 0 is 0. 0 and 1 is 0. 1 and 1 is 1. 1 and 1 is 1. This is a 0, and a 0. So what has happened here? So the second number with its ones tells us basically which of the numbers from the first number do we want to copy down into our answer. So there's a 1 here in my second number, which means this 0 comes down. There's a 1 here, which means this 1 comes down. There's a 1 here, which means this 1 comes down. And there's a 1 here, which means this 0 comes down. And everywhere where there was a 0, you just get a 0 in the answer. So the AND operation is a way to copy certain bits out of one number into another number. And that's what we can use here to pull out these pieces. We can use the AND operation to isolate just these 8 bits, and then the shift to bring them down. And over here, that's exactly what we're doing. I wrote this get pixel red, and it does an AND operation with a number that isolates the top 8 bits and then shifts them down by 16 positions to move it over all the way to the right. Same thing for green. I isolate just the 8 bits in the middle and then shift it down by 8. And then for the blue, all I have to do is isolate the lowest 8 bits, and then it's already in the right spots. And then for the other ones, for setting the pixels, same idea. Shift it to the left by 16 positions to put it in the right spot. For green, shift it by 8 positions. And for blue, you don't have to shift it at all. And I'm using OR in order to set the bits. So AND can be used to copy bits out, and OR can be used to copy bits in to a number. Okay, so that's what's going on behind the scenes when I am doing get pixel red, green, and blue. Okay, we might have time for 1 or 2 more programs. Let's see, what else can we do? Let's make the picture black and white. So we want to take this color picture and turn it into a black and white picture. Black and white pictures, even though they're composed of just grayscale values from white to black and gray, all the grays in between, they're still color images. It's just that the red, green, and blue components have the same value. So to make this picture black and white, we have to convert those red, green, and blue values from whatever they are to just be all the same. So one idea is just take the red, green, and blue values and just average them. Let me go ahead and make a copy of this. Copy image1.c to image2.c. The reason I'm doing that is because these 2 programs have a lot of the same stuff, like for loading the image in. It's just that loop in the middle is a little bit different. So let's go ahead and bring this up, and we're still loading the image in, creating an array. It's just that here in the middle, we're not going to do this. So we're still going to get the red, green, and blue pixel values, but now we're going to average them together. So we'll do red plus green plus blue, and then just divide by 3. In fact, I think if you Google around how to convert color image to black and white, that's not it. No, I want to do it like this is, I don't want this. I don't want like how to use some app to convert it, right? I want to do this like convert RGB to grayscale. I guess that's kind of like, yeah, here we go. Average the channels, average the red, green, and blue. Anyway, what I was looking for was there was a web page that I found, and they actually gave an incorrect formula for averaging. What they gave, and this is kind of silly, was they gave this: red plus green plus blue divided by 3. That is not correct. What's wrong with that?
Because of the order of operations, it'll do blue divided by 3 first.
Yeah, and then basically leave the red and green untouched. All right, so make sure you got the parentheses in there. Okay, so let's go ahead and try this. And we'll look at this. Uh-oh. That doesn't look right. Oh, I see. I computed the average, but then I didn't put the numbers, I didn't put that average back into the pixel. I put the red, green, and blue back in there. So we got to do like average, average, and average. All right, see that? Ah, looks better. Okay, there's our original color one, and there's our black and white one. That's not too bad. I'm curious though. Let's try it out with the scuba image. So here's our scuba diver, and then here's the black and white version. Not bad. But it turns out, although this works pretty well, it's not exactly what most human eyes would see. You know, inside your eyes, you actually have receptors for red, green, and blue. That's why red, green, and blue are the primary colors, not because there's anything intrinsically primary about the colors red, green, and blue, but because our receptors in our eyes are sensitive to red, green, and blue light separately. But each one of those receptors is slightly differently sensitive. One of them receives light much better than others, and that is in fact why, if you've ever looked at like a green laser light, it seems to be so much brighter than a red laser light, even though they're the same wattage, they're the same power of output. The red just appears to be dimmer than the green, because our eyes are not as sensitive to red as they are to green. And so if you look up, you can see that there's a formula for doing the conversion. And here's one of them that I've seen, which is you take the red component and multiply it by essentially 0.3, and the green multiplied by 0.587, and the blue multiplied by 0.114, and these are basically the factors that have to do with how sensitive our eyes are. So notice that green is like twice as sensitive as red, and blue is not very sensitive at all, about half as much as red is. So let's try this formula. So instead of just averaging them, we'll do red times 0.299 plus green times 0.587 plus blue times 0.114. That's the same as this formula here. So here's our, yeah, it doesn't look that much different than it did before, but supposedly this is better. Actually, let's do this. Let's change the code again. Let's have it do it on the burger. But I'm going to call this new burger 2, just so we can keep the old one around. So here's our original burger. Here's the one where we just simply averaged the pixel values. And then here's one where we did that conversion using those scaling factors. You can see, all right, it's just, I don't know if you can even tell on the recording, but it's just subtly different. There's some stuff going on over here. Let's see if I can, I'll just see if I can show more of this image. I'll bring this down.
Like more contrast between the two.
A little more contrasty?
Yeah.
It looks like, to me, it looks like you can see a little bit more in this shadow area than you could with the original one. The original one's just a little darker in here. Anyway, so that's supposed to be the way you do conversions. And there's some disagreement over these exact numbers. And not every human is the same. The reason why some humans are what we call colorblind is because these scaling factors are not the same from human to human. These are just kind of like the average among humans. But some people can't see, let's say, they can't distinguish between reds and greens very well. And that may be because these scaling factors are more equal than they are actually in you know, to other people. It's actually really fascinating why some humans are colorblind, and it's not so much because one reason is because their receptors are less sensitive to particular wavelengths of light. So they might have a receptor that's like red deficient or green deficient or blue deficient, and that means that they simply just can't see that particular color very well at all. And then other people have, well, I guess I can kind of draw a picture here. So we got wavelength of light here. Then there's supposed to be like, you know, here's your red receptors and your green receptors and your blue receptors are supposed to look like this. They're supposed to be separated peaks so that you can distinguish red from green from blue. But what happens in some people is they're not nicely separated like that. They may overlap more. So this particular person would have an easy job of distinguishing blue from anything that's red or green, but they have a hard time distinguishing red from green because those peaks overlap.
Is it possible to like make an image, like for a colorblind person, make an image, like code it in such a way that they actually can discern different colors?
Yeah.
Like the colors?
Uh-huh. So that was actually one of the first apps that a friend of mine downloaded on his phone when he got it, 10 years ago. He got an app for color because he's profoundly colorblind. He can still see some colors, but he has this problem where the peaks overlap, right? He can't distinguish between some colors very well. And so what this app did was it used the camera and it put up an image on the camera. But what it did is it took the things like the things that are green, and it basically shifted the colors on them. It changed the colors so that it essentially moved this peak over a bit. And so what I saw on the screen when I looked at it was like this garish image where there was lots of like oranges and yellows. But what it was doing is it was basically isolating the green stuff and transforming it into a different color that he could then see more clearly. So yes, you can do stuff like that. You can simulate what an image might look like to someone who's colorblind, who's maybe red-blue deficient or red-green deficient. Or you can enhance the color. We could take the greens and just boost them way up so that they're really bright green. But then someone who's a little deficient in the greens will see that as just being a normal green, even though it's really bright to everyone else.
That's really cool.
Yeah. So
Were you there when he saw like the colors like for the first time?
Yeah. He was like,
oh yeah.
He was like, I can see the difference now between these two colors, right?
That's so
you know,
cool.
it wasn't like you've seen those videos of that the glasses you can put on that make people see and who are colorblind see, right? Those glasses only work for people who have deficiency, not the overlapping. And so what it does is it filters out the other colors that they can see perfectly well, makes everything darker to make them more even. So it's kind of like if you are, let's say your reds work fine, your blues work fine, but your greens are a little lower. So what these glasses did basically is they just lower the reds and lower the greens to make everything equal, and then you can see the colors better. So things that are green now stand out more because their color's been better. What those glasses cannot do is solve this problem.
Okay.
So they only work on a subset of people that are colorblind. But yeah, he got that app and he's like, wow, this app is really cool because now I can basically distinguish colors that I couldn't distinguish before. And that's not to say he walks around all day with the app in front of his eyes. I mean, he only uses it when he runs into problems where someone says like, hey, look at that green thing. He's like, I don't know what you're talking about. To him, the world is just colored the way it is colored. And it's kind of like, can you describe the color red to someone?
Really?
No, you can't, right? You can make comparisons to other things. You can say, well, this color red is like this other color red, but you can't really actually describe what that color is. And so to someone who's colorblind, red is just red, right? It's just the red it's always been. It just looks different than to the rest of us. But I can't ask him to describe what red looks like. All he can say is like, well, things that are red look kind of like things that are green. I just have a hard time distinguishing between those two colors. And I said, well, that must make driving kind of like terrible, right? You can't tell a red light from a green light. He said, of course I can tell a red light from a green light. The red light's on top and the green light's on bottom. And he goes, and yeah, red lights and green lights are really bright, so I can tell the difference, right? I can see that they're different colors. But for things that are close, like you've got, a pale red and a pale green, he goes, those are just the same color. He says, but I get by it in the world just fine.
Christmas must be really fun.
He goes, for bright reds and greens, I can still tell the difference. It's just when they're kind of similar that I can't tell. He goes, but that's just my world, It's kind of like asking someone, asking someone who's in a wheelchair, what's it like to walk? I don't know. Never have done it, especially if they're born, not being able to walk. Let's see, do you want to do one more program with images? Let's see. I did. I asked the question, then I said, okay, let's go ahead and do one. Why don't we do one more, and then we'll just call it a day. Okay. So let's do one more. Let's take an image, and then let's see if we can flip it horizontally. Okay, I don't want to rotate it so it's upside down. I want to flip it so it's a mirror image of what it was before. The other way to think about it is, I want this pixel over here to be over here on the right, and I want this pixel over on the right to be on the left. And I want the pixel that's next to it over here to be over here, and I want this one to be over here. So what do I have to do?
It wouldn't be like the same as the reverse almost?
Yeah, we're just reversing an array of pixels. Exactly. Okay, so we don't have to fool around with the red, green, blue components. We're not changing the colors. All we're doing is changing the positions of the pixels. All right, so this pixel right here has an XY coordinate. This one has an XY coordinate. This one has an XY coordinate. I want to take the pixel that's on the left, and I want to swap it with the one that's on the right. And I want to take the one that's on the right, and I want to swap it with the one that's on the left. So the row number is not going to change. The Y value is not going to change. It's the X value that's changing. The X over here goes to the right, and the X is over on the right, goes to the left. Same thing for the ones in the middle, right? You're just swapping them with their corresponding pixels that are a mirror image of where they are. So we're still going to have this outer loop that goes from the top of the image to the bottom of the image. And we've got this loop that goes from left to right. But we're doing reversal. If you remember from reversal, we don't have to go all the way from left to right. We only have to go halfway across. So we're going to do width divided by 2. And now let's see if we can write the code in here to swap the pixel on the left with the pixel on the right. Any ideas?
You have to create a temporary variable to store one of the values, then swap the values and put the temporary value back in.
Good. So let's make a temporary value, and the pixel is just an integer, so I can just make an integer. And we're going to pull in pixels y x. And then pixels y x is equal to pixels y, and then what goes inside the second brackets here?
Is it width? It's width minus x minus 1?
Yes.
Or minus, and then parentheses x plus 1.
Yeah, exactly. And if you take away the parentheses, it's x minus 1. Yeah, so that's the same calculation we did for reversing the array of numbers. Why did we have to do this plus 1? So why isn't it just width minus x? Well, we just let's see. No, I don't remember. All we did was we just worked out the math, right? We just did some examples, and we saw we were always off by 1, so we had to end up adding 1 to the number in order to get it to work into the right spots. Okay, compile, run, and we should now have our original burger image. And I thought I was going to have where's my new image 3? Was I working on new image 3? Oh, here it is. New burger 3. Oh, I didn't compile the right program. Got it. Here. Ah, that's better. Here's our original. And here's our... Now, is that what you were expecting? Here's our original one. And here's our new one. So that seem reasonable? I do this every semester, and there's always at least one person that says, that's not what I was expecting. I was either expecting it to be just all wacky, or somehow in their mind they thought it was going to be like rotated and upside down rather than just flipped horizontally.
I mean, it's like a mirror image. So,
It is, yeah, it's exactly, it's a mirror image.
So I mean, it looks like it would if you looked at like a burger and then you had the mirror of it.
Mm-hmm. Let's try it with the scuba one. So here's our original. Oh, where'd it go? I accidentally closed it. Here's our original. And here it is flipped. So he's just swimming in the other direction. And all the lettering on his clothing is bound backwards. So hopefully that gave you a little bit of insight into what happens in Photoshop when you do those things. When you select flip left right, it essentially just did that code that we did there. When you do convert to grayscale, we learned how that works, and we also learned how to darken it. I think maybe one last thing we could do is what happens if we, instead of dividing by 2, what happens if we multiply by 2?
Share your screen.
Oh, sorry. Yeah, what happens if we multiply by 2 rather than divide by 2? Any predictions as to what's going to happen?
Increase the brightness.
Well, yeah, but what's it going to look like? Here's our original.
Wow.
Whoa, what happened there? There's our original. There's our new one. Why does it look so weird?
Well, I would imagine when we multiply the values, we may exceed the range that can be stored in each of those RGB values.
Mm-hmm.
And then I guess we'll be left with whatever bits can fit into that space.
Remember, when it reassembles the pixels, it just slams them right next to each other. So if let's say the blue component got too big to fit within 8 pixels, it essentially started bleeding over into the green channel. Some of the bits from the blue ended up in the green. And likewise, if the green got too big, some of its bits ended up in the red. So we end up with these kind of weird colors because we exceeded the 8-bit values that we could store in each one of those colors. Someone says, this is what the world looks like to bees. So to fix that, we need to make sure that after multiplying, we don't exceed the values. So one thing we could do is, someone suggested do a mod 256 on there. So if it gets greater than 256, then do mod 256, and that'll have the effect of essentially chopping off any of the high bits. And I don't actually need to check to see if the numbers have gotten bigger than 256 because the mod will work correctly even if the number is less than 256. So here's our original, and here's our, it actually doesn't look any different. So that's not really what we should do. The better thing to do is check to see, is the number now bigger than 256? And if it is, just clamp it down at that maximum number. So if it gets too bright, then just clip it at that point. If red is greater than 255, which is the biggest number, then just make it equal to 255. Same thing for the green. If green is greater than 255, then just make it 255. So here's our original, and here's our new one. And at least the colors aren't garish, but you can see we blew out all this bright stuff over here. It got too bright. We can't hold those values in the red, green, and blue pixel values that we have, and so it just gets too bright. But at least the colors are preserved. So you've probably seen this effect when you brighten up an image in like Photoshop. When you slide that slider over, the whites just ended up blowing out and you lose all the detail there. Now these days, some of those programs have individual sliders, one for brightening up just the shadow portions of the image. So anything that's darker than average gets brightened. Anything that's lighter doesn't get touched. You know, we could do something like that. We could look at the grayscale value and say, if this pixel is, let's say, darker than halfway, then go ahead and brighten it. But if it's brighter than halfway, just don't touch it. And they also have sliders for working on the highlights. So if it's a brighter pixel, go ahead and darken it. But if it's a darker pixel, just leave it.
That's really cool because I am a photographer on the side. I do a lot of editing in Adobe Lightroom. Mm-hmm. So it's really cool to see like how this is like crossing into computer science. What's going on in the software behind the systems.
Yeah. cool. I really like how there's like connections here. Gosh, if I had come prepared for this, we could do another one, which is to do the green screen effect. You seen that in video, right? So anywhere where there's green, you basically replace that green with something else.
Why does it only work with green, or is it, I mean...
So the reason why, there's also green screen, there's blue screen. There's two of them. And so the reason why it's done with green is historical. Back in the old days, before digital televisions and digital cameras, the color information sent with a television image, it was separated into, there was a black and white image sent, and then the color image was sent in separate, almost like separate channels. And it wasn't a red, green, blue image, it was kind of like red and green were sent together, and then blue and red were sent together. And so you could basically, you got your blue and greens combined with the reds. And so if you took those two channels and then you subtracted one from the other, that would isolate just the red and just the green and just the blue. And then you could turn that into the image that you see on the screen. So basically, they're able to send 4 channels of information: grayscale, red, green, and blue, in only 3 channels. Kind of cool. That's one little trick they did. But the other was, because the red and blues were sent together and the greens and reds were sent together, that meant that green and blue were the easiest colors to isolate out of the color signal. And so that's why green was chosen and is used for the green screen effect, because historically green was easy to pick out from the color information. Same thing with a bright blue, but green is used more commonly because people are less likely to wear bright green clothing. So once you got the green picked out, then it was also easy to basically chop off that color channel and then swap in the image from another television signal where that green was. Does that make sense?
Yeah. Thank you.
Somewhere in my massive files for assignments, I actually do have some green screen images that I used for one of my classes many years ago. They had, one of the assignments was, I actually got like almost like a production shot from one of the Avengers movies where the Avenger actors are performing in front of green screens. And then I had the students basically paste in an image of an explosion behind the actors, so it looks like they're running away from something that's exploding. So that was pretty cool. But all we had to do was just run through the pixels of the image, find something that was green, and just swap in the corresponding image from the one that you're pasting in. Gosh, I wonder if I can find those now. Now you got me curious. Now I gotta go look. I gotta go see if I still have those. It won't take me long to find out if I still have them. Was it here? Nope.
It's interesting because I was watching a video on like special effects in movies, and the YouTuber was comparing Black Widow's special effects to Dune's. I don't know if you've watched Dune. And the two movies, Black Widow, like you can tell it's definitely like obviously there's a green screen because the light is just not right exactly. Like, explosions and everything. But in Dune, they used sand-colored screens or whatever to reflect proper light. So it's kind of different from what we were talking about, but it was still kind of, it's just interesting. And
now with the way they do like the Mandalorian and Boba Fett is like totally different now. Now what they got is this set where they got a giant display that wraps around the actors as a big giant cylinder. And so they're able to project the actual background images. They're no longer using green screens. They just project the actual background images behind the actors. And they said the nice thing about that is, first of all, you don't get that green outline that they have to digitally remove later on, which means that you don't get a subtle like green highlight on their clothing. And it also means the lighting in the room is now perfect. Like if you're walking on the sunset, they've actually got a real like digital sunset behind you. So the lighting looks perfect and the shadows are projected in the correct way. And then also, what do you do about the parallax effect? You know, when the camera moves, where the actor is like moving across the frame, but the background is not moving. That's all now tied in digitally to the camera movements. So the background is also changing along with the actor. And so if you're standing stationary in that, it looks weird because the background is now moving in the opposite direction that you would expect it to move. But to the camera's perspective, it looks correct. I think you can find some YouTube videos on what they're doing now with this. But they said that like if you have the space to do it, this is the way to do it now because it's just better all around. Anyway, I did find some of the files that I had left over from that. Let's see. So here's the Avengers actors against their green screens. You can see that like it's not green all the way around. It's like there's just these green screens set up, but there's still some background here. And then here's the buildings that I wanted them to superimpose. And so they had to write Java code to do chroma key. Oh, and I also had a mask for them to work with. And what's this? Oh, that's just some greens. And you could also, they also had to do this. Superimpose the minion onto a street. So that's pretty easy to do. You just run through this image. If you find this green color, you just copy in this. Golly, we have some time. Do you want to do this?
Yeah, I'm down.
You're down? All right, let's put the minion onto the street scene. All right, let me copy these files in. Let's see. Oh, first thing I need to do, my graphics library only works with PNGs. So first thing I need to do is convert this to a PNG so that I can work with it. And then we have, oh, the minion is already a PNG, so that's good. Let me see if I can drag this in. All right, we got our green minion, and then here's our street. First things is these images need to be the same size in order for this to work correctly. You can see these are very nicely. I made these the same size. Let's get rid of all these over here. So we're going to have to load both of these images into memory at the same time. So let's change this. Let's load in street.png, and we'll call this BKG, background. And then we'll also load in what's called the key. The key is this one here because it contains this green area. Now, I already know that the two images are the same height and width, so all I have to do is just get the height of one of them and the width of one of them, and I've got the other one. So width and height, let's do this for the background. And now we need to create an array of integers to hold both of the images. So I've got key pixels, and I have background pixels. Okay. And then we'll fill in background pixels. We'll fill in those two arrays. With the pixels from the key image and the background image. Okay, so we're now going to loop through the pixels like we did before. We're going to go from top to bottom, left to right. And then, so what do we have to do here? We need to look at the color of the pixel. And if the color is that green color, then we'll go ahead and copy in to our new image the background pixel. And if the color of the pixel is not the green color, then we'll leave it untouched. So we're going to basically take our green image here, and we could do this one of two ways. We could either create yet a third image, a third new image, and then copy the corresponding pixels into it, or we could use this key image here and just replace the green colors with the background colors. Do you have a preference as to which one you want to do? Do you want to create a third image and then it either copies from the green image or the background image as appropriate? Or do you want to have just two images and we're just going to replace this green color with the background image?
Maybe like just the two images.
Just the two images? Okay. So we'll say replace green color in key image with corresponding pixel from background image. Now, the way I've set this up is this is like a pure green color here. This is, as far as the colors go, it's all green and no red and no blue. So we just have to look at the pixel value and see whether it is a pure green color. So we can say if key pixel of y and x is equal to, and now a pure green color, I think actually I've got a pure green color in here. It's this, RGB green is this value. This is the hexadecimal value where you've got, oops, sorry, I didn't want to scroll that here. You've got 00, that's the blue value, 8 bits of blue value. FF is 8 bits of green value, and 00 is 8 bits of red value. So we'll use this constant here. So if the key pixel is that pure green, then replace it with the corresponding background image pixel. And if it's not this pure green, we'll just skip over that pixel and move on to the next one. Okay, and then we'll create a new image from the existing pixels. So this is called new image, and we'll use key pixels here, and then we'll save it as Minion Street. Okay, so let's take a look at this again. Actually, let's go ahead and just compile it and run it, and we'll see if it works. Uh-oh, I have a bug. This should be Pix. Oh, goodness gracious, I have semicolons here. That's an error. Defines do not have semicolons on them. Use of undeclared. Oh, package pix. That's not right. Package pix. Where is it? Background pix. Background pix. Here it is. Oh, there we go. Okay, image is 600 by 338. Here is our minion. And here is our, uh-oh, that didn't look right. Oh, let me see. that did not work out the way I thought. Let's see, key pix yx equals background pix. Maybe this is not a pure green. Maybe this is not as pure green as I thought it was.
Could you write a method that checks the pixel, like this pixel has that color? Can you write a method that returns that value and then just put that into this one?
Well, so the way I constructed this, I made this pure green here. So this is a very uniform green. So maybe what I could do is I could just print out the pixel value of this like top left one.
Yeah.
And then we'll just use that in our program. I think that's what you were saying, basically.
Yeah.
Okay. Oh, this is the number. And that's actually the decimal number. Let's print it out in hex. Let's see what it is. It's 1FF13. So it's not a pure green. The green channel is that pure green color, FF, but there's just a little bit of red, and there's a little bit of blue in there, or green. Blue. Yeah, so it's a little bit of red, pure green, and then a little bit of blue. So we'll use that number. Okay, let's take a look. Here's our original one, and we're close. We're close. So these colors here are just not quite that green. They're close to it, but you get the general idea about how this works. So what we'd have to do there is find out whether find colors that are close to that green color. I don't know, we could do something like, if this is maybe greater than, I don't know how exactly we would do that. How do you define a color being close to another color? To do it realistically, what we'd have to do is basically use the distance formula in 3 dimensions. We know what our target color is, and then we have these other colors that are like, again, if you picture this as being like a cube, you got your red, green, and blue components. You've got this 3-dimensional space that pixel resides in. We know what our target color is, and what we have to know is the pixel we're looking for close to that one.
This reminds me of calculus.
Essentially, it's a distance formula. How far is this pixel from this one that that is our target one? If that's within a certain range, then we know that's the color that we want to replace. Someone here says, I have an idea. Check to see if the green is a lot bigger than the red or the blue. That might be like a kind of an easier way to just accomplish the same thing. Because again, if you picture this as kind of like a volume, if the red is this way and the blue is this way and the green is this way, then the green is all the way up there at the top, right? It's all the way at the top, and the red and the greens and the reds and the blues are just kind of like dancing around that in a little space. So maybe we can do that. So we'll pull out int red equals, what was that? Get pixel red of the key pix. Oh, sorry. Key pix y and x, and int green equals get pixel green. Blue and then we can do like if green is greater than or equal to let's say 250, right? So it's way up near the top. The green is really bright, and red is, let's say, less than, I don't know how well this is going to work. We'll try it. $200 maybe, and blue is less than 200. Okay, so if the green is really high and the red and blue are darker, then go ahead and swap it in. Oh, it's better. It's better, less fringing than we had before. If you've been doing video work for a while, this is a common problem you had. You had the green screen behind the actors, and then right at the very edges of them, where the pixels are not pure green and they're not purely the color of their clothing, you get this problem where it can't identify whether that's a pixel to replace or not. So you end up with this kind of green halo around them. And you still have this problem. And so what some of the current video software does, like OBS and Wirecast and some of the hardware consoles, is they take a second pass through the image once they've replaced the green, and they look for colors that are close to that green, and they add the complement of that color to it. So they look on the color wheel, where is that color, and then just add to it the color that's on the opposite side of the wheel, and that has the effect of canceling out that green and basically subtracting it out of the image. So what they do is they do edge detection around where they put that, they did edge detection between where the green was and where the green wasn't. So they find that edge, and then for all those edge pixels, they basically add the complement of that color to it and cancel out the green effect. And that's actually one of the settings you can find in OBS, is how wide is that edge piece and how much canceling do you do. in order to eliminate that green fringing. But I think this is pretty close. I mean, it gets the idea, hopefully, across about what's happening. Let's see, another idea was make sure that green is bigger than red and green is bigger than blue. So if green is greater than red and green is bigger than blue, see what happens. Oh, whoops. Oh, it's close. So we got a little bit of a little problem right here. So this problem of what do you do right at the very edges is a continuous problem, even today, with modern hardware and modern algorithms. What do you do exactly with those fringes around the edges? And then I had those other images, the Avengers ones. There's our Avengers. There's the buildings. I want you to superimpose them. And then there's also a mask, which shows you what part of the images contain the green screen and what part of the images just contain background stuff. So that was a three-part process, which is look at the green values, determine if it's one of these green values. And here you had to take into account the fact that some of these greens are in shadow and some are not. So you're working out this calculation. Is it close enough to the green value? And then you check to see, is that in this mask area? If it is in this black area, the mask area, then you replace the green with the background. And if it's in this white area, you just go ahead and replace it with the background. Don't do the green screen effect. And so this allows production crews now to just screen off parts of the stage and not have to completely coat the whole thing with green. Let's see, did I actually come up with the solution for this? Here's what it ends up looking like if you wrote the program correctly. So you start with this, superimpose the background using the mask to tell you whether to do the green screen effect or just copy in the background, and then you end up with that picture. You still have that green fringing around it, but it's close enough. Close enough to get the idea. Comments?
No, that's really interesting.
Yeah. What did you find most interesting about it?
I like seeing the real world application of how do you take these abstract programming concepts and then do something real with it.
Yeah, it's really cool, like seeing, because I've always wondered about that, like, you know, watching the news or how movies do that. It's like, how does that all work? So it's really cool.
Yeah, good. Well, you've given me some ideas for some more assignments to do, right? Well, now you know how to do the green screen design, but maybe next semester, instead of doing your reverse game, we can do the stuff with the green screen. That's kind of cool. All right, so that's what I wanted to do with you today, was just go over some of these array manipulation, working with arrays. So we got all this boilerplate stuff at the top and the bottom for pulling the image data into the array. The real meat of the program was right here in the middle, working with the arrays themselves and looping through all the pixels. Maybe what I need to do is further wrap up the libraries and just say, we'll have one function that just simply loads the image in and it constructs the array for you, and just, there you go. So you don't have to deal with all this stuff up here at the top. Any other questions? So next time, Tuesday and Thursday, we're going to start diving into pointers. We haven't really seen pointers, but they are a core part of the C programming language. It's one of those things that exposes to you, the programmer, which other programming languages like Java and Python tend to hide from you. So I think it's really important to learn these, not only because in order to become a proficient C programmer, you have to understand how pointers work, but also learning how pointers work will give you a little insight into how these other languages that hide them from you are actually functioning behind the scenes. Arrays and pointers are intrinsically tied together. You've already seen that in the visualizer we've been using, that when you pass an array into a function, you're not passing in a copy of the array, you're passing in a pointer to the array so that the function works on the original array itself. When you pass in something like an integer or a double, you get a copy of that variable. So that if you change that variable, it doesn't affect the caller. That's not the case with arrays. When you pass in an array, you get a pointer to it, and that means the function that is operating on the array affects the caller's memory. Huge difference there. Why do they do it this way? Because it's faster. When you pass in just a pointer to an array, you're just copying over 8 bytes of information, the address. If you had to pass in a copy of the array might be huge, and it would take a long time to make a copy of it. So the original designers of C decided for larger data structures, anything larger than the primitive types, anything larger than integers, doubles, floats, and so forth, will be passed in using a copy, using a pointer rather than a copy of it. And that also leads us into, as someone pointed out, malloc, being able to do dynamic memory allocation, to be able to set aside memory while the program's running, and that memory is not on the stack. It's in that area called the heap. That allows us to now create chunks of memory that persist beyond one single function call. As it is right now, if we try to create an array inside of a function, we can't pass it back to the caller because that array disappears. It goes out of scope. We'll learn about dynamic memory allocation, which lets us set aside memory for an array and then have that memory persist once the function exits. So that's coming up pretty soon as well. So we got pointers to learn about, and from my experience, most people will probably not get pointers right away. And so don't feel like when you get to the end of the chapter about pointers that if you don't understand it, you're not going to be able to do the rest. I think what it takes is continuous, regular exposure to pointers and using them for the pieces to all kind of like click into place. I've had a lot of students say like, I don't understand them yet, I can't move on to the next chapter. And my answer is, go ahead and just move on to the next chapter, and you'll start seeing pointers being used in different ways. And then maybe that'll help kind of form the whole picture that you need, because you can't get it all at once. You have to just be shown it continuously in many different contexts before it all kind of makes sense. Now, the people who might have a slight advantage is people who have taken the assembly language course. I'm not real sure whether you did things like pass pointer arounds in the assembly language, but if you did, you kind of have a better idea about what's going on, because you're putting addresses into registers and then passing those to subroutines rather than putting values into registers and passing them in. So if you did architecture class and it involved pointers, then you may be a little more familiar with what's going on here. Abdul on YouTube says, yes, it does take time to understand pointers in C. So if it still feels confusing after 1 or 2 weeks of working at it, don't worry, you're actually on your way. Okay. Well, have a good weekend, everyone. Remember,
Right.
You too.
Thank
Monday
you.
Monday is a holiday for us. So if you have a Monday, Wednesday class, it's not going to meet. Oh, by the way, they've lifted the restriction on online classes at Sierra. So if you had a course that was supposed to be in the classroom but went online at the beginning of the semester, you're now back in the classroom. Or actually, it's up to the teacher, I think, but the recommendation is you be back in the classroom. So if you had, let's say, a science course or an English course that was supposed to meet in the classroom but had to go online at the beginning of the semester, then expect next week to go back into that classroom. You should get a notification from your instructor about what's going on. Now, these courses will stay online, so we'll be right here. Okay.
Well, thank you. Have a good weekend.
You too.
Yeah, thank you.
Have a good one. Bye-bye. Okay, folks on YouTube, I hope you got something out of that. That was a like brilliant stroke of inspiration that someone suggested doing the green screen stuff, and I was able to pull some of those examples out of stuff I did many years ago, and we were able to use that. So that was really cool. It was nice to see that used in a different context than before. Okay. Well, I hope you all have a good weekend. I won't be here on Monday, but I'll be back on Tuesday, and we'll start in on pointers in the C language. So have a good weekend. Take care. Be safe. Bye-bye.